Let's go back to our ramp situation and let's see if we can figure out something interesting about these graphs as they relate to the mathematical models. When I say mathematical model, I really mean equation, but let's draw it out and see what it looks like. So here's our ramp. I'm going to put a cart on the ramp, but I'm going to put the cart about halfway up the ramp. And it's already moving, having been pushed sometime previously. So as it's here in the middle, it's moving up. It's going to slow to a stop at the top, and it's going to come back down. And I want to know what the position, velocity, and acceleration graphs for this look like. So again, one of the things we want to do, we want to set our zero line. The easiest way to do this by far, easiest way to do this is put the zero line at the far left edge of the ramp. That way, every position is going to be positive. The way I've drawn the graphs, all positions are positive and all times are positive. Here, velocities can be positive or negative, and accelerations can be positive or negative. But let's do it this way. So, first question, where is the cart? Look, it's right there. It's not at the zero, it's somewhere in front of the zero, which gives us an indication as to the initial position of the cart. And what happens to it? It moves away from the zero line and then all the way back toward the zero. Because it's the position graph and the ramp is here, so ramp equals constant acceleration. So this is linear, this is horizontal, linear, this one's a parabola. Starting position is here, ending position is at the zero. What does it have to look like? So it's got to be a parabola. What about the velocity? Well, there's two things we're going to analyze. One, we're going to analyze the actual motion of it to start, and the second thing we're going to analyze is the slope of the velocity graphs. Because remember, to get the velocity values, you look at the slope of the position graph. But let's start here. All right? It's here, it's moving which way? To the right or to the left? It's moving to the right, so we decided earlier that the positive motion was this way. So it starts with a medium positive velocity, slows to a stop at the top, turns around and it has negative velocities. Here it has medium negative velocity, and then when it gets to the zero, it has a large negative velocity. So, starts medium and positive, zero, medium and negative, large and negative. What would that look like? Well, if it starts medium and positive, then zero, then medium and negative, then large and positive, we know it has to be linear. Let's see if that goes with the slopes. For the velocity graph, there it has some medium-sized positive slope. At the very top, the slope of a tangent line is zero, which corresponds to zero velocity right here, then medium and negative, then large and negative. How do we get to the acceleration graph? Well, there's two ways. We can analyze the ramp itself, and we can analyze the velocity of the slope of the velocity graph. If I just go and I analyze the slope of the velocity graph, what do you notice about the slope of this line? Two things. It's constant and it's negative. Therefore, the acceleration is probably constant and negative. When I look here, this ramp slopes down and to the left, which means the acceleration is constant and negative. So, acceleration is constant and negative. So what I like about this is, conceptually, we can understand each of these three graphs, what they look like in relationship to this here. One of the things that's really interesting is that we can come up with equations for each of these that are actually kind of relevant. And let's start with the bottom here. So what do we know about the acceleration? It's constant, and it has the value a for acceleration. Now that value happens to be negative, not that big of a deal. So we could say that the acceleration is equal to a. I know a equals a looks kind of inane, but it is a constant, and I'm okay with that. What about this velocity graph? What about this velocity graph? It has the form y equals mx plus b, or v is equal to something, okay? But what did we decide about the slope of this? The slope of this graph is the acceleration. So if we just start with the y equals mx plus b idea, well, what's on the y-axis? That's the velocity. What's on the x-axis? That's the time. And then we're missing our two variables, our m and our b, which are slope and our intercept. Well, tell me about this. What did we decide the slope of the velocity graph was? What's our definition? The slope of the velocity graph is the acceleration. That's the point. The slope of the velocity graph is the acceleration. And what about the b value? Well, what is the b value right here? The b value is the velocity when? At time 0. So we denote it like this. v0. So the velocity value is equal to the acceleration times time plus the initial velocity value. What about the position equation? What about the position equation? Well, we know it's a parabola. It's going to be of the form ax squared plus bx plus c. But what I like about it is we can figure out some values for these things. So when we go to put in the values that we know,
Juniors, please go to the gym for your class photo.
the things that we know that are cool are, first of all, what's on the y-axis? It's our position. On our t-axis are the times, so it's something t squared plus something t plus, well, what is the c value in this case? The c value is the position when the time is 0, which means that this is the initial position. That is the initial position. What about these other two? Okay, what about these other two? Well, I think we're going to do a lab, or maybe you did a lab, or you looked in the textbook, but these two have very specific coefficients that go with them. It turns out that the coefficient in front of the t term is actually the initial velocity. Actually the initial velocity. And, interestingly, the coefficient in front of the t squared term is 1/2 a, is 1/2 the acceleration value. So these are two equations that are going to be important for us to know, remember, understand, and memorize. This one for sure. And this one. Those actually appear on the AP equation sheet. But the AP equation sheet can look like hieroglyphics if you don't already have a good understanding of these things. But there's really a couple more, and I'm going to see if we can't work on these couple more here. One thing that's important before we go too much farther is this idea. So I have the position here, that's the position at some time t. This is the initial position. And what if I wanted to know the change in the position over some time. In this case, we're going to do the total change in position. So when I look, that's the initial position. In this case, because this car ended up back down here, the final position is all the way back down here. That's the final position, because the cart went on the position axis away and then ended up toward. How do I find the change in position? So we always use a little triangle. It's the Greek letter delta. It means change. And it always means the final value minus the initial value. That's the procedural content of it. And we have a name for this. The change in the position is called the displacement. And it really is just you take the final position minus the initial position. If you're only moving in one line, it might be similar to the distance. But in this case, the car went away and then came back. So it's just the difference between the final and the initial. In this case, something that's interesting is that this cart ended up farther to the left than it started. So its displacement would actually be a negative number, which is totally fine. But that's the displacement. So one of the ways that we're going to see this equation is if you subtract x0 from both sides, you may see it written like this. You may see it written like that.